Okay, so at this point, we've talked pretty extensively about all the different types of instrument systems that help you navigate, help you monitor to the engines, and help you fly the airplane. Uh, there are actually, that's probably only about half of the instruments that are on the plane. There is a lot of instruments that are designed to keep the airplane safe. And so now we're going to dive into that, from ILS to radar altimeters and how they work, to GPWS, ACARS, all those types of systems. Not all of these systems are going to be widely disseminated across the spectrum of aviation. A lot of them are going to be largely concentrated in the heavy commercial world. But as you start to go down the tiers from heavy commercial into business aviation, you'll see some of those systems go away, but a lot of them will stay the same. And when you get to general aviation, kind of your top tier general aviation will have some of these systems. But as you continue to go down to down to your J3 Cub on a grass strip, you won't see hardly any of these. So take that into consideration as you kind of digest the information and assess like where you want to take your career and what is important to pay attention to. Now, a lot of this will manifest on the written test for sure. Probably not so much the oral and practicals, but as those tests change, we'll just have to see what comes up. So it's best to have a good understanding of all of them as you go through.
Okay, so we're going to start this by talking about the instrument landing system, commonly referred to as ILS. Now, you can see the graphic in front of you that's straight out of the 8083. There's a lot going on with the ILS. It's, on to relative to the pilot or to you, the mechanics, and they're trying to troubleshoot something. It's just one instrument. But there's actually several components to that system that are all basically crammed into one instrument. So there's a lot going on. So don't let this like overwhelm you. What we're going to do is we're going to take it apart piece by piece, and then we're going to talk about every single piece. And at the end, we'll put it all together and say, okay, this is what an ILS actually does. All right. So, what's the purpose of an ILS? So, an ILS is there to take you. Imagine like an airport that's completely socked in. There's just all uh, clouds or fog or whatever you can't see, and you've got to land. You're up there. You're about to run out of gas, and you got to find your way down. Now, you got a couple of options. You can make a visual approach. You can come down. You can't see anything, and you can just hope that you miss the ground, that your altimeter is calibrated correctly. You didn't make any mistakes, and you just kind of like put it in slow flight and make an easy descent. And hopefully, if you miss the runway, you can just do a go around and miss it. All right. That is not advisable. Matter of fact, it's illegal because it's super duper dangerous. The only way that you can actually make that landing is through an instrument approach. All right, and the instrument approach leverages the ILS to basically talk you into to think about like radio waves grabbing the airplane and steering it so that way it lands perfectly on the tarmac of the runway as it comes down. Now, in order to do that, you'd have to control the horizontal movement of the airplane and the vertical movement of the airplane to make the perfect landing. All right, and so we have a lot of math that's been done on how to land an airplane at the perfect way, the perfect time, the perfect you know uh, angle that it's coming in to touch down on. We've programmed that into several different radio transmitters on the runway, and then optimized the airplane to receive those radio signals, and then distill it down into a single instrument that allows the pilot to fly the airplane correctly, even whenever they can't see anything out and they're just a couple hundred feet above the ground to come in and then roll out and land perfectly. All right, now those parts and pieces I was talking about are the localizer, the glide slope, compass locators, marker beacons. All right. Now we're going to take these apart and go piece by piece, starting with the localizer. Okay, so what you're looking at, those little red T-like antennas right there, is the localizer antenna. You've probably seen them before at larger airports. They have a radio navigation approach, an RNAV approach for a major runway. They're pretty standard at your fully mature airports that you'll find. You won't find them at small GA places. We do have them here in Texarkana. Matter of fact, this exact system is part of the reason why we had to push the runway extension from 26 to 27. And it's because there's only a handful of people that can actually move that system, and they're booked out until then. So good business to be in if you're looking for a different career other than aviation maintenance. Anyways, so how does the localizer work? All right, now I'm going to read this right out of the 8083 and then we'll talk about it. It says two modulated signals are produced from a horizontally polarized antenna complex beyond the far end of the approach runway. They create an expanding field that is 2.5 degrees wide, about 1,500 feet, at 5 miles from the runway. All right, so let's go to the whiteboard to help us understand that.
Okay, so localizer. So let's say we have a runway. So that's our runway. What the localizer is going to do is going to produce not one, but two horizontally posed signals that go out, right? And so if you're looking at dead on like this, they're going to go out like this. Out to 5 miles. So imagine you're an airplane that you're coming in. You're going to intercept that localizer and be like, oh, I'm to the left or I'm to the right. You're going to make adjustments. And as you come in, it's going to funnel you in. So if you were to look at it from the top down, which makes it a little bit easier. There's the end of your runway. You've got you'll have to forgive my artwork. Something like that coming in. So the airplane comes in, it's going to say like, hey, look, I'm right. But if I start to drift, it's going to say, hey, look, I need to come back this way or that way. And you can kind of walk your way in right down to the touchdown point. Okay. Now, so that is what the localizer does. So localizer is like left to right. Like it's only really caring about like if the airplane's off to the left, off to the right. All right. It does that by using two horizontally poled antennas, so horizontally lobed antennas that are being broadcast out to the world, all the way out to 5 miles. So the idea being, like in the old days, is that you could approach and be a little bit off. Like they wouldn't really expect you to be like just super right on the center line. It'd be cool if you are, but if you're not, they've kind of accommodated that. You could be off a little bit to the left, a little bit to the right. And then you catch the localizer and then you just move the plane where it needs to go to get lined up with the runway.
Okay, so this is the localizer in the plane. It's actually just a needle that runs up and down this instrument here, and as the plane gets lined up on the center line of the runway, it will also center up. Now, if it gets off to the left or to the right, that needle will also drift to the left or to the right. And so you could have a situation where you are, if you think about it like trying to shoot a bullseye, that's exactly what you're trying to do. Once you're on glide slope and you're on the localizer directly, it'll be a perfect cross in the very middle, and it'll be basically like shooting that little circular marking in the center there. All right, so now let's talk about what the glide slope is. Okay, so this is going to be the weirdest antenna that you see all day, but that is a glide slope antenna that you're looking at right now. So let's see what the 8083 has to say about the glide slope. All right, so the vertical guidance is required for an aircraft to descend for a landing that is provided by the glide slope of the ILS. The glide slope provides the vertical guidance for corrected angle of descent. Radio signals funnel the aircraft down to the touchdown point on the runway at an angle of approximately 3 degrees. The transmitting glide slope antenna is located off to the side of the approach runway, approximately 1,000 feet from the threshold. It transmits a wedge-like pattern with the field narrowing as it approaches. And this is what they're talking about. Now, if you can imagine an airplane that's coming in, if it's too high, the glide slope will let them know. If it's too low, it will also let them know. And the idea is to try to hit that perfect balance point so that you're at the right angle to the runway to make the perfect touchdown right there at the threshold. And this is like one of the bigger components of your ILS system, because left or right you can always abort that landing and then come back around. But like if you get too low, that could make it really dangerous for you, especially if there's any sort of obstacles out there that you're going to be flying into. If you're too high, then you're just in a kind of a go around situation. But yeah, so that's why the glide slope is so important. Okay, so this is back to our instrumentation in the cockpit. That glide slope needle is the horizontal needle. If you get too low, it's going to indicate that, hey, look, I'm too low. If it's too high, it's going to go up and say, hey, look, like you're too high. So you always want to be on the glide slope for any approach. You want to be like right there at that perfect angle coming in, so that way you can touch down. And this is how we do that with instrumentation whenever you're in a low visibility situation. Okay, so let's look at the original graphic that we first looked at. A lot of this starts to make a little bit more sense to us. You can take a lot of the words out and just kind of look at the pictures and understand exactly what's going on. The two that we haven't talked about yet are the compass locators and the marker beacons. All right, so you can think of they co-locate together. They're in the same spot generally, and what the compass locators do is just allow you to find the glide slope. So here we're gonna read it out of the 83. So the compass locator is a transmitter designed for the purpose to help the pilot intercept the ILS to enable its use. There's typically one located at the outer marker beacon at 47 miles from the runway threshold, and another may be located in the middle marker beacon about 3,500 feet from the threshold. The outer marker compass locator is a 25-watt non-directional beacon with a range of about 15 miles. It transmits a omnidirectional LF radio wave keyed with the first two letters of the ILS identifier. The ADF receiver is used to intercept the locator so that no additional equipment is required. And if the middle marker compass locator is in place, it is similar but is identified with the last two letters of the ILS identifier. Once located, the pilot maneuvers the aircraft to fly down the glide path to the runway. So essentially, if you're looking for the glide slope of the runway, you'll simply tune the ADF. You'll track into to the compass locator, and then you'll wait for the glide slope to kick off and go crazy, and you'll know that you're actually you're on the ILS, and then you just make the adjustments as necessary. Now the outer marker and the middle marker basically allow, or the marker beacons, they allow for you to know that you're still on the glide slope. So this is what the 883 says about it. Marker beacons are the final radio transmitters used in ILS. They transmit signals that indicate the position of the aircraft along the glide path to the runway. As mentioned, an outer marker beacon transmitted is located 4 to 7 miles from the threshold and transmits a carrier wave modulated with 400 hertz audio tone and a series of dashes. The transmission is very narrow and directed straight up, so that way when you cross it, you're like, okay, I know where I've crossed it, and you can't get really that confused about it. Marker beacon is receiver receives the signal and uses its light to light a blue light on the instrument panel. This, plus the oral tone in combination with a localizer and a glide slope indicator, positively locates the aircraft on approach. So that way, whenever you cross over that middle marker or that outer marker, you'll know exactly where you're at. It'll flash at you, and it'll give you a tone. You're gonna say like, okay, I know exactly where I'm at. And you can look at the approach plate on or your map and say, this is where I'm at. I'm doing good. I'm coming on down. And all this is to basically allow you to navigate flying into a runway with no visual acquisition whatsoever. Now there is a point you're going to hit that's about 200 feet off the ground where the decision height alarm will go off, and you'll have to look up and say like, hey, look, I can see the runway, I can make the runway visually, and I'm below the clouds, and I'm going to come on down and land. Or if you can't, then you have to call a missed approach, and there's a whole other procedure that goes around that. But then you just basically put all of this back into back in action one more time. And that's how an ILS works. Now, as a maintainer, your job will be to install and to maintain bits and pieces of this, depending on what your job is. You're not necessarily going to be like quizzed ever on like exactly how does the ILS work, but what you do need to know is how this operates, so that way you can understand how it integrates into the rest of the airplane, or the rest of the systems rather. Okay, so let's look at an ILS on a 737 Max. It's not really that different than any other airplane, honestly. You'll have a marker beacon antenna that ties into MMR1, which handles all your VORs and stuff. There's a close relationship between the VOR and the ILS. We won't go into that. It's just unnecessary information. Anyways, but so that's what the antenna looks like, and that's where it goes. You notice that it routes to the REU, so that way it can produce sound, and then to DPC2, it'll push out to the flight displays up that way. It also has a role on the HUD, because the HUD will have the instrumentation for the pilot to see. So instead of it going to DPC2 and then on to the primary flight display, the MMR will go right to the HUD, so that way if there is a DPC failure or a flight display failure or whatever, you still should be able to land the airplane via the HUD, since it's directly tied into the system, and you don't have an integrator box that stands in between the two of them. The diff dial also is going to record that, because that's recording all your flight data, to let whenever you crash the airplane and they come get the diff dial and they're like, okay, well, what happened? They'll know that you weren't on glide slope, or whatever the thing may be. The only other thing to really kind of point out here, I mean, you have this cool graphic on the top left hand side that basically shows you the airplane going through that, but it's no real different than any other airport out there. This one has a inner marker beacon, which is kind of interesting. But the one that's really different is your marker beacon lights off to the right. If you look, there's outer, middle, and inner. Inner, the only time you're going to get that is at a Class 2 airport. But the one that I want you to pay attention to is the functional test light that comes up. Now, most of this, as a maintainer, you won't ever mess with, but you absolutely will be messing with those functional tests on a regular basis. There's in the AMM, you'll go in there and they'll say like, hey, look, this is the functional test for this system or that system, or whatever, and you'll go through the steps, and it's pretty simple. The display will kind of walk you through that, and then you'll get a pass. Sometimes, depending on the environment that you're working in, sometimes you seeing the pass is enough for you to go sign it off. Sometimes they'll want a printout, so there's a printer that's installed into the center console of the airplane, and you'll hit print. It'll print out a little sheet that says like, hey, look, this test passed. You'll show that to your quality assurance people or quality control people, whoever they are, wherever you are. But like, know that like a lot of these systems is kind of giving you the academic knowledge of understanding how it works. But what it looks like in real life is that you're going to go and do a functional test, and whenever that functional test passes, then you're good to go. If it fails, then you're going to start troubleshooting the functional test, and say like, okay, like, well, what could potentially be wrong? Do we have an antenna problem? Okay, what's our antenna look like? Do we have an MMR problem? The good thing with a lot of these systems, notice that it says like integrated multi-mode receiver 1 or DPC 2. You can just simply move those, take DPC2 out of its slot and DPC1 out of their slot and swap them and put them in there, or MMR1 and MMR2 and swap them and put them in there and rerun the test and see if you get the same one. Because since it only goes through IMMR1, if the MMR is the problem, then and you've moved it, then MMR2, which is now an MMR1 slot, will show you, hey, this test passed, you have a bad MMR, and that's what you need to replace. If you do all that and all of it still fails, then you're into a situation where you're looking at like, well, what's going on with the wiring? There's some sort of connection problem, and that's how you really troubleshoot these advanced avionics. Like, you're going to turn around and say like, okay, assume the computer is doing something ridiculous, and like you need to get it fixed. And then you're going to swap them around, and then whenever they fail, then you're going to go to wiring after that. And this is assuming your switchology is correct. So like all your switches are set right. You've followed the test correctly. You don't have any sort of external circumstance that's weighing in on it. Then you'll go to the computers. Then you go to the wiring, and then a lot of times that's where you can start playing with like voltage drops and a lot of the more technical ways to see what could what's causing the failure. Voltage drops specifically because a lot of this is signal voltage. You're talking about like half a volt might make the difference between a 1 or a 0 in that computer, and if you have just enough corrosion to slow a signal down or drop the voltage just enough, it could actually cause a failure. But yeah, so that's ILS, and let's move on to the next system. Okay, so before we really get into the next system, we have to talk about another piece of equipment that should be familiar to you because it does come up in movies and things like that. But that is the radar beacon transponder, or simply known as the transponder. So for each aircraft equipped with an altitude encoder, the transponder also provides the pressure altitude of the aircraft to be displayed adjacent to the on-screen blip that represents the aircraft on the ATC controller. So, what is a transponder? All right. So, on a radar screen, whenever like ATC is looking at it, and ATC being air traffic control, all they have this big screen that has maybe some overlayment that shows like a runway or obstacles or things like that. And then all of a sudden, like an airplane will appear on it, and it'll be a little blip, and it'll have a circle with an arrow stuck on it, showing its direction of travel and its relative rate of travel. And you'll see that, and you'll just know that it's just an airplane, but you don't really know anything about it. You don't know is it a small Cessna 152 or is it a 747? Like who is it? Where are they going? What's their intentions? There's just no real information about it whatsoever. Well, the transponder helps inform ATC and everybody else about what who you are and where you're going and what you're doing. Now, whenever you contact ATC and you say, "Hey, look, I want flight following. I'm a VFR flight," or if I want to file an instrument plan or open an instrument flight plan, they're going to give you a what's called a squawk code, and that just is a four-digit code that goes into the transponder on the airplane. And so, like the for most flights, they're going to follow visual flight rules, and so you'll squawk 1200, and you also have the ability on most transponders just to press the VFR button, and it'll just automatically go to 1200 because it's so common. Now, you as a technician need to know the three emergency squawk codes, and then what VFR is. So VFR will always be 1200, and so that, like you said, you can hit that button, it'll go to 1200, or you can dial it in yourself. The three that you need to know to either only use whenever you have to, or just avoid altogether, is 7500, 7600, and 7700. 7500 is on this chart in front of you. It says unlawful interference. That's a fancy way to say the plane has been hijacked. And so if you're ever on a plane, say you're a fly-along mechanic, and somebody comes and puts a gun to the pilot's head and says, "Take me to Cuba," or wherever, then you can reach up there and squawk 7500, and then without any radio transmission whatsoever, ATC knows that somebody is hijacked or otherwise done something to the airplane that needs to be dealt with. That's a quick, fast way to get a F-16 to come by and escort you wherever it is you need to go. The other one that is a lot more common is lost communication, is 7600. So like what will happen with that is that the radios will go out, and then you'll put in 7600 into the transponder. That allows ATC to see that your radios aren't working, and then you'll do things like flash your landing light or whatever, and communicate to them, "Hey, look, I'm trying to communicate with you, but I don't have any radios." They will then come back with a light gun and then get you on the ground, so that way you can deal with the issues. Now, some of this is kind of like it's not going to go away, but it's just kind of been replaced with cell phones, because a lot of times you can just call ATC and be like, "Hey, look, I'm in such and such of an airplane. We're flying along, and we lost our radio." And they're like, "Okay, cool. We'll come in and we'll do light guns for you," or whatever. And so, like, this whole system is kind of designed pre-cell phone, and it's just stayed there, and because there's no real reason to replace it. And then 7700 is just an emergency code. And so, like, if you're in an emergency and you declare emergency, time, time allowing, ATC will tell you to squawk 7700, or you can just do that if you're in a situation where you absolutely need to get on the ground, and maybe you couldn't talk to them or whatever. But yeah, those are squawk codes that everybody should know that's in aviation, pilots and mechanics, because you either need to avoid accidentally putting them in, or B, you need to know when to employ them. And usually they're posted next to the transponder in most airplanes, but it's not a requirement. Okay, so let's just look at some transponders. That big gray brick right there is what transponders used to look like. They were very analog, and they would go click 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 whenever you would turn the numbers. But right now it's squawking VFR. It's squawking 1200 or 1200. But that's the old analog style transponders that you'll still see. You'll still see in aircraft, especially in GA aircraft, because transponders generally don't go bad, and they're expensive to replace. So unless somebody's having a panel redone or some sort of major avionics work, a lot of times they'll just leave those older transponders in there. Here's a little bit more common one. It's this one you'll typically see in experimental aircraft. But like you notice that there's the VFR code, or VFR button right there. You can immediately squawk VFR. This one is squawking 7,000. And it's going to give you an altitude reading because it's altitude encoding. We'll talk about encoding here in a minute. But notice the switch there. You have off. You can put it into standby. You can put it in ground mode, and then on, and then you can put it in altitude mode, or alt. Now, if you forget to put it in altitude transmitting mode, which I've done before, ATC will come back and ask you like, "Hey, look, is your transponder working? What's your altitude at?" Because one of the things with an altitude encoder is it's supposed to tell ATC what altitude you're at, so they can deconflict the airspace so you don't run into anybody. And so if you're flying along and you don't have it on alt, then like you're not really doing that, even though you might have a transponder that does do that. So that being said, make sure you follow your checklist if you're going to go flying. For us on the ground, where that will make a bigger difference is whenever we start to test them. If you're in a facility that's certificated to do that. But yeah, that's one of the more modern versions of a transponder. Okay, so this is a GTX327. It's probably one of the most common transponders that you'll see out there. Notice that ALT is highlighted on the display, letting you know it's on altitude mode. It's squawking VFR at 1200, and the flight time is indicated right there. Whenever ATC tells you to enter in a code, you simply just type in the numbers like you would like a calculator or anything else like that. You go to altitude mode by pressing the alt button. You can put it on standby. You can squawk VFR. The only thing that's really fundamentally different than this one is that it has an ident button. So that ident button at the top left-hand corner, what that's doing is that like if a ATC controller comes and says, "Hey, squawk 1234," and ident, then what you'll do is press that ident button, and what it does on his screen is it lights it up, it causes it to flash, so that way he can find you really, really easily and see where you're at. That seems to be less common these days when you go flying. I haven't heard anybody say ident for a while. It might be because ADSB is out and about, but you can still do that if required. But the GTX 327 is probably one of the most common general aviation transponders out there. Okay, and so this is what it looks like on a G3X, which is the new. Will eventually replace all the G1000s probably in a century, but um, this is what it looks like now. And that notice that that's a touch screen, and so you just go to the transponder and you just type it in right there, and then you have your modes where you can do standby, ground, altimeter, and then there's an ident button at the bottom center, so that way you can ident if they ask you to. But you can fly along, press the transponder screen, it'll come up, and you just type it in. Now, the transponder in the old days, or even with a 327, it's the whole box is the transponder, and it goes to an antenna. With these displays like this, the display is just the interface, and then usually there's like a little box that will be mounted somewhere behind it, that is the actual transponder. And usually they just get all tied in together at the screen and go their separate ways on the backside of it. But yeah, so that's what it looks like on a fancy GA aircraft. Now let's talk about modes, transponder modes. Okay, so we're not going to mess with mode A, but we are going to talk about mode C, mode S, and ADSB. Okay, so mode C transponders were kind of like the standard for years. Mode C transponders came out. I think it was probably like in the 80s, if I remember right. And they're the ones that transmit the majority of the data. Notice the message length is 12 bits. If you can remember back to doing like number systems and talking about binary and what a bit is, that will make sense to you. The frequencies are actually kind of important. Not that you'll ever change it or deal with it, but notice that you only have like 1 hertz up or down worth of tolerance on a transponder. If not, it's no good. It has to be adjusted. Now, every 2 years, a transponder has to be a transponder check, and it has to go to a Class 3 radio station or a MRO or shop that has a Class 3 radio license to do that check on there. So that's a pretty common thing. Not overly expensive. They just check and make sure that's good. And because the reason being is pretty simple. If you have a transponder that's not working and you fly into a busy airspace, one controller might be able to see you, but the next controller may not. And so whenever they hand you off, he basically just sent like a chaos bomb into the middle of his traffic pattern, and you don't want that. The big thing with the mode C though, notice that this is use cases is pressure, altitude, and extraction. Now, what that means is that like it is actually going to transmit the altitude that the plane is at. So it's like, hey, look, hey, here we are at this height, and off you go. Because the pilot could be wrong, or it could have some sort of wrong data. But the likelihood of the transponder is going to transmit an incorrect altitude is very, very low. It'd have to have a problem with the pedostatic system, or it's an air data computer, one of the two, to be able to do that. Which has also it's a risk that's been mitigated through other checks that happen. Anyways, so mode S transformed or basically replaced the mode C transponder probably about 20 years ago. This rough numbers to bear, just bear with me. But the notice the message length gets a lot bigger. All right, it's because we were able to figure out, hey, look, this is how we can transmit more data. And then not, but 4 or 5 years ago, ADSB became kind of like the standard for the way that we transmit all of our data, and we're going to talk about ADSB here in just a little bit. Okay, so this is what the transponder looks like in a 737 MAX. You're going to see this graphic here, and again here in a second we talk about TCAS, and so I won't go into it too much detail. But notice that the transponder is quite large on these bigger airplanes. And then they still have a control interface up front, just not any different than the G3X system that we just saw. The G3X is a nice fancy display that goes to a little small kind of like amber colored box behind the screen. On a 737, you have a very 737-esque styled transponder controller there that goes to a very, very big black box in the back. Anyways, notice that it feeds information to and from the TCAS computer and takes information from the ADARU 2. The reason being is that it has to get its air data from somewhere. Its altitude primarily it's going to encode and transmit. Also notice that there's two different antennas to it with coax switches in between. And so if you end up having a TCAS fail or a transponder fail or something like that, oftentimes the problems are going to be with the transponder itself, the box, or there's going to be some corrosion or something in the antenna. But yeah, so that is what it looks like on a 737 MAX. Okay, TCAS. Now, TCAS stands for Traffic Collision Avoidance System. There's TCAS 1 and TCAS 2, and we're going to talk about it. So, TCAS 1 came out and was developed to accommodate the general aviation community and regional airlines, little airplanes. The system identifies traffic in 35 to 40 miles out and issues advisories to assist the pilots in visual acquisition of intruder aircraft. TCAS 1 is mandated on aircraft with 10 to 30 seats. If you got over 10 seats, you're going to have to be TCAS enabled. Now, TCAS 2 is a more sophisticated system, and it's required on internationally on aircraft that have 30 seats or more. So most of the heavy commercial aircraft that you guys are going to end up working on are going to have they're going to be TCAS 2 aircraft. TCAS 2 provides the information of TCAS 1, but also analyzes the projected flight path of the approaching aircraft. So that way it's going to say like, hey, look, this is where they are, this is where they're going to be. So that way you don't fly into where they're going to be and actually cause a wreck as opposed to just avoiding them. So if a collision or a near miss is imminent, the TCAS-2 computer issues a resolution advisory, an RA. This is an oral command to the pilot to take specific evasive actions, like descend or whatever. The computer is programmed that such the pilot in the encroaching aircraft receives an RA for evasive action in the opposite direction. So, like if me and you are flying at each other, and my TCAS computer is going to be out there looking like where is this other guy, and then they're going to see like, oh hey look, there he is. My computer is going to tell me to descend, and your computer is going to tell you to ascend. So that way we avoid one another. And that's what's cool about TCAS is that they say they interrogate one another. That basically that two airplanes can talk to one another and make a decision or a recommendation rather as to where to go. Now the graphic in front of you is going to kind of like outlay like some ranges, right? So if an aircraft is coming into your little bubble where you're at, if he's within 20 nautical miles for both TCAS 1 and TCAS 2, that is going to appear on the TCAS screen or in on the nav screen of a 737, which we'll look at here in a second. It'll pop up and it looks very similar to a blip on a radar screen for ATC. Now you will get a traffic advisory if it comes within region 2. That is going to be 3.3 nautical miles away from you. Hey, look, this guy's like really close to you. You need to start taking some action. If it comes within 2.1 nautical miles, that's where the resolution advisory gets issued and the pilot's told to take it back. That's where it's going to tell you to go up or go down. Now, this also, it's not just horizontally, but also vertically. So if you look at the bottom part of that graph, the TCAS regions are laid out for the vertical separation between the two. Now, RVSM will probably have a little bit to say about this, but that's still very, very close to one another. And so that's something that we'll talk about here in a little bit. Is a reverse vertical separation. Anyways, so that's what TCAS is. Now let's look at it on a 3.7, see what that looks like. Okay, so this is the same slide that we just looked at a second ago with the transponder, but this is the rest of the TCAS system. Or at least you understand it now to see how it goes. In order for TCAS to operate correctly, it has to know what altitude you're at. That's why it's integrating the ADRUs and getting information from them. It's also then looking at the transponder and to say like, hey, look, like where are we at, where are we going, all that good stuff, and then it's using the ATC antennas that are on this aircraft to broadcast and receive signals from other aircraft. And so once the signal is received, it goes to the TCAS computer. It makes a decision, and then makes that will then push out to the transponder to do X, Y, or Z to tell the pilot to command or issue a traffic advisory or whatever. Okay, so this is one of my favorite systems. This is the Automatic Dependent Surveillance Broadcast System, or ADSB. All right, what is ADSB and what does the 8130 have to say to us? Collision avoidance is a significant part of FAA's next-gen plan for transforming national airspace system. Increasing the number of aircraft using the same quantity of airspace and ground facilities requires the implementation of new technologies to maintain a high level of performance and safety. That's a long-winded way to say that the airspace is getting steadily busier as time goes on. The successful proliferation of GPS has led to the development of a collision avoidance system known as ADSB. It's an integral part of the Next Gen program. The implementation of its ground and airborne infrastructure is currently underway, and ADSB is active in parts of the United States and around the world. So this has probably been written a pretty good while ago. ADSB is mandatory for most aircraft now. There are situations where you don't have to have it, but for the majority of operations, you're going to have ADSB to operate in certain airspaces. All right, so how does it work? So essentially, the airplane is going to get a fix on itself, and then it's going to transmit that fix along with its altitude and speed, and a couple other things. Transponder code or transponder codes and ADSB don't necessarily integrate, but it will transmit that data out, and it is received by other aircraft, and so other aircraft will see that and say like, oh, like here we have another airplane coming in. So that divides the system into two halves. You have ADSB out and ADSB in. So ADSB out combines the positioning information available from its own GPS receiver with an onboard flight status to include the altitude, velocity, and time, and then it broadcasts this information back out to other ADSB equipped aircraft and ground stations, primarily air traffic control. Now, ADSBN is a whole new beast. So this is actually really cool from a GA pilot's standpoint. Not only will ADSB basically tell you there's somebody coming with you, but if you have the right technology in your plane, you can also get onboard weather. Because since they're transmitting these signals back out, they're also going to grab all of the AWOS weather that's local to you, and they're going to transmit it, to you. So that way, what you, before you used to have to either call or kind of interpolate or have some sort of expensive weather radar or any number of other systems. Now, for about $500 or $600, depending on like what kind of Guardian you have, we'll talk about that here in just a second. You can get all that information on an iPad inside of your plane, or even on the panel displays right there, so you can see where weather is progressing in real time. You can see where aircraft are coming in real time. There was a couple weeks ago, I was flying up from Shreveport, and there was a guy that was basically flying down from Shreveport, and we were at the same altitude. And I noticed that, like, as I started to descend to try to get away from him, he started to ascend to try to get away from me, and we ended up passing each other with probably like 2,000 feet between us. But it was interesting, but whereas not that long ago, that would have been a flight service would have called and told me to move in theory. Uh, but now we can kind of make those decisions on our own, so that way it deloads a lot of the ATC traffic and also enables me to make my own decisions as I go along. This is all really really cool. It's also really interesting because this system is more kind of focused and slanted towards general aviation as opposed to like heavy commercial aviation. So it's kind of cool to see the innovation happening at the kind of with the little guys first, and then because the bigger commercial aircraft have about a dozen systems to help prevent them. ADSB is good and all for them, but like it's not really going to add as much safety as it will be for the smaller general aviation aircraft. Okay, so this is what's called a Sentry. Now, this mounts to a suction cup that goes on to the left hand side of your window as you're flying along. And what it does is it allows you to, without an STC or anything crazy, it allows you to transmit your ADSB data out to anybody else that's around you. And so, like, you'll be able to pull up an iPad and be able to see. You see those little wedge marks on the screen there. Those are other aircraft, and it also will calculate that little blue ring that goes around the airplane that tells you, hey, look, based on your height and your altitude and your type, this is where you could feasibly glide to if you lost your engine right now. So there's just tons of really good data but that has been able to be integrated into platforms that have come around in the past couple of years, primarily for flight. And so you'll see these out in the field being integrated more and more, or more or less retrofitted on older aircraft. The new panels that come in don't have the need for this because they have the same ability, based on their internal technology. But yeah, this is a super cool for general aviation. It kind of gives a airline level of data fidelity and safety to a Piper Cherokee from 1967. Okay, let's talk about radio altimeters or radar altimeters. I always say radar altimeters because that's what they call it in the Army, but you're not wrong saying radio altimeter. It's basically the same thing. Effectively, what this is just sonar for the aircraft, but it's not using sonar; it's using radio waves. If you'll notice in the bottom right-hand corner of this artificial horizon display, you have a string that says DH200, right? Now that means decision height 200. So you're at 200 feet above the ground. It's time to make a decision. That data is being fed to the display from the radar altimeter. What the radar altimeter does not care about pressure, does not care about density altitude, doesn't care about any of that stuff. It is going to simply like emit a signal, hit the ground. It's going to bounce up. It's going to say like, okay, well we are because of that time. We are 500 feet above the ground, or we're 1,000 feet above the ground, or whatever the thing is. That's really important for helicopters. It's really important for commercial aviation that is coming into land because that will 100% like be or the radar antennas will 100% be displayed and inform the decision of the pilot as they come in. So that's something that you may have to contend with one day. Even though I haven't seen them really go out, they seem to be pretty reliable once they're installed properly. Okay, so this is what the radar altimeter architecture looks like inside of a 737 Max. You notice that there's two antennas, one to transmit, one to receive. They're both going to be up there next to the nose underneath the aircraft. Or not next, right next to the nose, but under the 41 section there, where kind of the arrow's pointed, that's about where they're at. The antennas are there, but then they immediately route up to the radio altimeter transceiver. Just kind of build our radio terminology is because it also transmits a signal and receives it, even though it's talking to itself effectively. Anyways, and you notice how that radar altimeter actually goes out to everything else. It's going to go to DPC2 to end up on the flight screen, and it's going to be able to be controlled by the EFIS control panel right there. But it also feeds all of those other systems that you see, just a couple of them, like the weather radar, the ground proximity warning system, HUD, FDARS, TCAS, DFCS, all of those systems uh, feed off of your radar altimeter. Now, the thing is, you don't necessarily have to have it to fly. And I would be curious to see a 37's MEL list if it was a deadlining item or not, or if you could defer it to the next next maintenance. But it is definitely very, very helpful for a lot of different things to know exactly how high up you are, rather than trying to judge it or guesstimate it. Because keep in mind, like flying like a Cessna 172 and judging the distance to the ground, it's not really that hard because you're so close to it. But in a 737, you're several feet up off the ground. Like so, whenever you extend your landing gear, it's way down there. It's way low. And then you're going to be flying, commercially. So it means like in a lot of different weather systems where you would otherwise just be like, well, I'm just not going to fly. Well, you're flying such a big airplane, and the mission is high priority to try to keep that schedule taken care of. That they fly a lot in areas or in times when you otherwise probably would just be on the ground, and so having that radar altimeter there is extremely useful for that. Okay, another fun system that you'll find mostly only in heavy commercial aircraft is the ground proximity warning system. Now, the 737 Max is the graphic that you're looking at here. Obviously, it has the enhanced ground proximity warning system. It means that it's just basically been enhanced more or less. And so the GPWS takes a lot of different uh, inputs in from a whole host of different systems. Anything that could potentially jeopardize the plane close to the ground, it's going to take an input from, and then give a warning to the pilot. So anytime that like you see on the movies, you hear this like this or terrain. That's what's screaming at the pilots. Anything from the landing gear being up either when they're too close to the ground, or down, or too far away from the ground, or if there is a certain situation where the flaps don't need to be on. They'll get a flap inhibit light that will come on. Gear, terrain, runway, all of these different very ground specific type conditions. The GPWS will alert the flight crew through it, and so you can look at the inputs area on the bottom left hand corner, and all the stuff, all the places it grabs information from, makes a decision, and then pushes out to the RU to alert the pilots, or to the HUD, or to the DPC to push up to the displays. And it also is going to be taking a lot of information based on the weather radar. That's the first time we've actually talked about the weather radar. We're about to talk about it a lot more. It actually, will inform the GPWS and let the pilots know that, hey, look, this is going on. But also, it takes a lot of data from the ground proximity warning module that basically says, hey, look, this is the state the airplane's in, and this is the height it's at. And it makes a decision and to alert or not alert the pilots. Okay, so here is another one of our little miscellaneous safety systems is the weather radar. Now, there's not a lot on the aircraft that is just kind of like inherently dangerous. I mean, aside from the engines and things that are just overly obvious. But the weather radar is something that can absolutely like make you have a really bad day if you were to walk in front of it while it's running. Now, a lot of systems are set up so that way if the airplane is in ground mode, it'll basically disconnect the weather radar and just allow you to test it, not allow you to fully run it. But some systems will allow you to turn the weather radar on while you're on the ground, and it could be a hazard to people that are around you. Kind of a fun fact: the way that people discovered microwaves was a guy working on a radar dish on a Navy boat had a Snickers bar in his shirt pocket, and he walked in front of the dish while it was on, and it melted the Snickers bar completely. And then he realized that, oh, look, we can use these microwaves to actually heat and warm food and things like that. And that was the birth of the actual microwave, the appliance. From him working on a thing that made microwaves the particle wave. Anyways, so that just goes to show you that before we get into talking to weather radars, just know that they are dangerous for people that are walking around in front of them while they're operating, and you need to take that into consideration as you do it. Now, that being said, there are three different types of weather radars. There's actual onboard radar for detecting and displaying weather activity, which is what that antenna in front of you is for, that you're looking at on the display right now. Lightning detectors is another type, very common and oftentimes integrated into the first. And then satellite or other source weather radar information that is uploaded to the aircraft from an outside source. That's not what we're going to talk about. ADSB will allow that to happen, as well as several other types of technologies that aren't as widespread, but if you have the money, you can buy them. But what we really care about today is the onboard weather radar systems, and they can be found on aircraft from all sizes. They can be from the smallest aircraft to the largest aircraft. It's almost kind of a guarantee that the larger the aircraft gets, the more and more that they become common. It's more uncommon to have it on smaller airplanes, but they do exist. They are happening. They function similar to ATC primary radar, except the radio waves bounce off precipitation instead of aircraft. They're just kind of dialed in differently. Dense precipitation creates stronger return than light precipitation, and the onboard weather radar receiver is set up to depict heavy returns at red, medium returns at yellow, and light returns at green on a display in the flight deck. Very similar to just watching the Weather Channel. That's Doppler weather radar. This is simply like a mini version of that, so that way the pilots can see in real time what's directly in front of them and make sense of it from their perspective. And what they're trying to do is trying to just avoid running into any sort of heavy thunder cell where there could be like turbulence, lightning, so on and so forth. Things that just generally aren't bad. Something to take them out is that radar can detect wind shear. Now, so next question is like, what's wind shear? Wind shear is whenever the wind is going differently at a high rate of speed in two different directions, very close to one another. So imagine this, like if you had two boards that were stacked on top of each other, and you were to grab either end of the board and pull out, so the way they went from being stacked on top of each other to not stacked on top of each other really fast, and that friction in between kind of builds up. That's effectively a shearing motion. Okay, wind shear can do the same thing. Now think about this. What would happen to an airplane if half of it was in one air mass and the other half was in the other air mass, and then that were to happen? And this is a machine that you have to calculate the maneuvering speed on the ground before you go off, and you could be like, hey, look, we can't make any abrupt turns above a certain speed. All right, and let's say that you were flying really close. Say it's 100 knots. That's your VA speed. All right, that's what maneuvering speed is called. Let's say that the wind is going 20 knots in either direction. Well, you fly through that wind shear, and then on one end of the airplane, you're exceeding VA at 120 knots because it's going one way. But on the other side of that threshold, the airplane is only doing 80 knots because it was under VA, and the air and the wind's going in a different direction. And then think about the tension in the middle of that plane, where like one end of it is going way too fast, and the other end of it's going a lot slower. And what would that do to the airplane? And there have been crashes because of wind shear. Weather radar has the ability to detect that and to avoid it. All right. Now, the other type of onboard weather radar system that you're going to end up encountering is a storm scope or a lightning protection system. All this effectively is that as the lightning pops, it generates an intense electromagnetic signal, which is picked up via a loop-like antenna, like the ADF antenna. Sometimes they use the ADF antenna, and it plots it on the storm scope relative to where the aircraft is at. Now, these are increasingly getting more and more integrated into displays, so you might have its own independent scope. But there are older airplanes that have these storm scopes on it, and this is what they look like. Okay, another system that you'll see, and this is purely limited to large heavy commercial aircraft, is ACARS, the Aircraft Communication Addressing and Reporting System. It's a two-way communication link between an airliner in flight and the airline's main ground facilities. Data is collected in the aircraft by digital sensors and transmitted to the ground facilities. Replies from the ground may be printed out so that appropriate flight crew member can have a hard copy of the response. All right, so here's the idea behind ACARS: is that, like, let's say you had a engine that was running low on oil, but it wasn't so much that it caused some sort of catastrophic response from the pilots, like they need to land immediately. And so what it would do is it would send an ACARS message to where it's going, and alert the maintainers, hey, look, have oil ready whenever it lands, or something to that effect. Like, it's really, ACARS is kind of, it's like one of those, it was a good idea, but I don't know exactly how well it actually ends up working. Now, the intent behind it was to eliminate downtime of the aircraft, specifically at the gate, so that way if there was an issue, the all of the prep work would be done by the time the plane landed up and shut down, so that way the work could get done and they could turn it around. So as time goes on, and as more digital means of communication, higher bandwidth levels of communication come become available, you can bet that there will be like an ACARS 2 that will come out, and so something to note. You will have to do ACARS tests on like pre-flight and things like that, so that's something to keep in mind. Okay, so our last little system we have to talk about here is the emergency locator transmitter. Now, what you have in front of you is an ELT. That you'll typically find them in the tail section of the aircraft, and they are shock activated. Now, you can turn them on and turn them off if need be, but like once they're armed, the thing that actually turns it on to start transmitting its distress signal is some sort of shock. So a hard landing can turn those things on. So it's always kind of a good practice. If you have a really hard landing, go to 121.5, which is the frequency they transmit on, and listen just to see if you set your ELT off. Sometimes, if you're like in a flight school or an area that has a lot of air traffic come through, the tower will actually call that flight school and say like, "Hey, look, you have an ELT going off," because they can tell about how far away it is. But a lot of times that doesn't happen. Now, what happens whenever the ELT goes off? All right, let's look at a graphic right quick from. Okay, so when the ELT goes off, it's going to start to transmit a kind of a homing beacon, like a pulsed, beacon. So like beep 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 beep, and what that's there to do is to help search and rescue locate the downed aircraft. Now, ATC monitors this frequency all the time, and so they'll know that an ELT has been set off if they're within range of hearing it. And they might try to call you or whatever to try to see if you make sure it's not just a hard landing or some sort of defective equipment or something like that. But if it's a legit crash, what's going to happen is they're going to kick the Civil Air Patrol out, and they'll start doing a grid pattern search or trying to home in on this beacon. And then once they get there, they'll start talking the ground guys on to come and recover the airplane if they can't land there directly. Which I've never seen a Civil Air Patrol helicopter, so most likely they're going to be on comms with the guys on the ground that are just going to drive up or walk into where you're at. There's a sea of other things that also happens. Like you'll notice on the graphic that you have the LEO satellites. LEO stands for low Earth orbit satellites, which is COSPAS and SARSAT. They'll also register the LT as going off, and then send that information down to the ground stations, and then out to the search and rescue people, so that way they can know exactly where it's at. So you have a multiple ways that the ELT will actually help you be found. You won't crash an airplane in the continental United States and get lost. Like they're going to find you. There's just too many people and too many ways for people to find you. Now, if you go out down in the Indian Ocean or something else like that, they'll know the general area that you went into. But if they don't get to the ELT soon enough before it runs out of batteries, which is going to be hard because you're out in the middle of nowhere, then maybe you're lost there. But anyways, that's what the whole purpose of an ELT is. It's really not that complicated. Things that you should know is that they have to be checked biannually. So like every other annual, you have to do an ELT check and or change the batteries on it. Once the batteries dip below 50% of usage, it's no good. It has to get changed, and then it also has a 2-year expiration date. It has to get changed every 2 years, and so. The other thing is that you can test the ELT, but it has to be the top 5 minutes of every hour. So if you wanted to test it, which an annual check is going to call for you to test it, all you're going to do is turn the aircraft radio on to 121.5, wait for the top 5 minutes of the hour, have somebody else back there in the back of the airplane flip the switch up, you'll hear beep, 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 and then you turn it off, and then you're good to go. And then you can sign it off and move on.